Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over how to verify trigonometric identities. Before we get started, we're going to take a look at some identities that you need to remember in order to be able to verify the trig identities that will be presented in this tutorial. Okay, so you need to remember your reciprocal identities. Alright, so what are your reciprocal identities? Let's start with sine. Sine x upon reciprocation is the cosecant function. Okay? So if sine x is equal to 1 over cosecant x, it follows that the reciprocal of the cosecant function is 1 over sine x. Okay? And then how about cosine? Cosine x is the same thing as 1 over secant x. Let's write that again. So cosine is 1 over secant x, which follows that secant x is 1 over cosine x. And then lastly, we have the tan and cotangent functions. If you reciprocate the cotangent function, you will get tan. Okay, so cotangent x is equal to 1 over tan x, since tan x is equal to 1 over cotangent x. So these are your reciprocal identities. You need to know these in order to facilitate your identity proving process. We then have our quotient identities. There are 2 of them. Quotient identities are nice identities that can help you rewrite tan and cotangent in terms of sine and cosine. So tan x is equal to cosine x, sine x over cosine x. And its reciprocal cotangent x, as you would expect, will be the reciprocal of this quotient right here, which is cosine x over sine x. Okay? And then the last set of identities that you need for this presentation are your Pythagorean identities. Alright, so what are your Pythagorean identities? The first one is sine square x plus cosine square x equals 1. And then we also have the one that relates tan and secant. 1 plus tan square x is equal to secant square x. And then lastly, the one that relates cotangent and cosecant. 1 plus cotangent square x equals cosecant square x. Alright, so if you have these formulas memorized, you'll become extremely easy for you to prove or verify trigonometric statements or equations. Okay, so let's take a look at some examples. These given identities are already true. You're just verifying that they are true. Okay? Alright, so the task is to verify the identities. Question 1, we have cosine x secant x is equal to 1. Now, what does it mean to verify the identity? It means to show that the left side is exactly equal to the right side. Okay? So can we make both sides of this equation identical, like the word identity suggests? That's the goal. Okay? Now, when you have the product of trig functions just like this, an easy way to verify a trig identity will be to write the functions in terms of sine and cosine. Okay? So can we rewrite it in terms of sine and cosine? Uh, the first trig function is cosine, so it's already in a desired form. Secant needs to be processed. So what is secant x? Remember we talked about this? Using the reciprocal identity, secant x can be written as 1 over cosine x. So what we're going to do is we're going to make a substitution, okay? So we're going to write cosine x times, instead of secant, we're going to substitute its reciprocal identity, 1 over cosine x. The question is the left side equal to the right side? On the left side, the cosines divide out, and you end up with 1 is 1 equal to 1. Absolutely. So we've been able to prove that this identity is true. Alright, let's take a look at another example. Question 2. Let's say we have the equation cosine square x over cotangent square x equals sine square x. Is this equation true or false? Well, it's already true. Well, we're just going to verify that it's in fact true, okay? Alright, so let's see. How do we do this? Remember earlier, we stated that if you have just trig functions in this format, no minuses or pluses, if you try and express every single one of them as sine or cosines, only it will be easy to achieve your verification of the identity. So let's go ahead and do it. First of all, let's rewrite these. If you notice where the squares are placed, what these represent, basically cosine square x, means that you have cosine x raised to the second power. But the standard way of writing it is cosine square x. Okay? So don't let that confuse you. And then cotangent square x is the same thing as cotangent x raised to the second power. And then sine square x is just sine x raised to the second power. So is this quotient on the left equal to the right? Now, we already have cosine square x. Cosine square x is already in the desired form. We need to change cotangent. To do this, we are going to be using our quotient identity. Okay? Cotangent x is equal to cosine x over sine x. So we're going to be making that substitution. So we have cosine x square divided by, we're now going to replace cotangent with its quotient identity, which is cosine x divided by sine x. And don't forget to square it. Okay? Now the question is the left side equal to sine x squared? Alright, now we have a complex fraction on the left. To simplify this, we're just going to drop, change, flip. But before we do that, let's simplify the bottom a little bit further. So we have cosine x squared, and then in the bottom we have a situation where we will apply the power of a quotient property, so that this becomes cosine x, the numerator square, divided by the denominator square. Okay. Is this equal to sine x squared? Now you can see the complex fraction situation I was speaking of earlier. Alright, now what we're going to do, let me divvy up my workspace. We're now going to drop, change, flip. On the left side, we're going to multiply the numerator, cosine x squared, by the reciprocal of the denominator, quotient, which is going to be sine x squared divided by cosine x squared. The question is this equal to sine x squared? Take a look at the left side. What do you notice? If we express cosine x squared, or cosine squared x, As a quotient, you notice we can divide out, right? Cosine square x goes here once, and cosine square x goes here once. And you're left with sine, we can rewrite it as sine square x using the standard notation. Is it equal to sine square x? The answer is yes. We've been able to prove that the identity is in fact true. Alright, let's take a look at question 3. What if we have the identity sine square alpha minus cosine square alpha equals 2 sine square alpha minus 1? Okay, so let's see. Here we have squares and an operation, namely this difference. When you have squares and a difference or sum, think about using the Pythagorean identities to prove your identity. Okay? If you take a look at the left side and the right side, you notice that on the right side of the equation, we have only one trig function, namely sine squared alpha. Whereas on the left side, we have sine squared alpha and cosine squared alpha. So the question is, can I replace this sine squared alpha with some expression that involves only sine? The answer is yes, because if we have only sines on the left side, we can see how we can manipulate them to get this form on the right. So my goal is to eliminate cosine by substitution with an expression that has just sine. Now think about the Pythagorean identity that involves sine and cosine. We talked about that earlier. It's sine square x plus cosine square x equals 1. Now what happens when I isolate cosine square x? So I can substitute that for cosine square alpha. So I can achieve that by subtracting sine square x from both sides. And that gives us cosine square x equals 1 minus sine square x. So this is another variation of the first Pythagorean identity. So what we're going to do now is we're going to replace cosine square x with 1 minus sine square x. So we're going to have sine square alpha minus parentheses. Now you have a minus here whenever you're making a substitution. After a minus, don't forget your parentheses to avoid signs with errors with sign distribution. So instead of cosine square alpha, I'm going to replace it with 1 minus sine square alpha. And the question is this equal to 2 sine square alpha minus 1? Is it? Let's go ahead and simplify. On the left side, we have a minus. Imagine as though there's a 1 here. So we're just distributing that to both terms in the parentheses. So what happens? We have sine square alpha minus 1 times 1 is minus 1. Minus 1 times sine square alpha is plus sine square alpha. Now is this equal to 2 sine square alpha minus 1? Sine square alpha and sine square alpha are like terms. Think about it as you have 1 sine square alpha and another 1 sine square alpha. What happens when you add two things that are identical? Well, you get twice as much, right? So when you add these two, you are going to have 2 sine square alpha minus 1. Is that equal to 2 sine square alpha minus 1? Absolutely. We've been able to verify the given identity. Alright, let's take a look at question 4. What if we were to verify that for secant square x over tan x equals secant x cosecant x? Okay. Alright, so now we don't have any sums or differences, so we won't need to use the Pythagorean identity here. So let's see. The strategy for situations like this is just like question number 1 and 2 is we are going to express everything using sine and cosine only. Okay? Simplify it as much as we can and see if we can achieve an identity situation. Now, what do you want to remember here? You want to recall that secant x is what? 1 over cosine x. Tan also needs to be replaced. Tan x is sine x over cosine x. And then we also have a cosecant hiding there. Cosecant x can be replaced with 1 over sine x. Alright? So let's carry out our substitution. If we carry out our substitution, we're going to have in the numerator, instead of secant x, we'll have 1 over cosine x. But since there's a square there, we're going to be squaring the entire situation. The numerator will be squared on the left side over tan. Tan x is sine x over cosine x. And then on the right side, secant is 1 over what? 1 over cosine. And cosecant is 1 over sine. Now on the left side of the equation, let's use the quotient property of exponents to simplify this. We'll have 1 square, which is 1 divided by cosine x square, which can be written as cosine squared x. They're the same thing. And then that divided by sine x over cosine x. The question is this equal to 1 over cosine x times 1 over sine x? Is it? Well, we have a complex fraction on the left side, so we're going to drop, change, flip. We'll multiply the numerator, 1 over cosine x square, by the reciprocal of the denominator, which is sine x over, actually we flip the denominator, right? So we drop, change, flip. If we flip the denominator, we'll have cosine x over sine x. Now, is this equal to 1 over cosine x times 1 over sine x? Is it? Now on the left side, we can break this cosine x square x up. We can write that as 1 over cosine x times cosine x times cosine x over sine x. Is this equal to 1 over cosine x times 1 over sine x? Is it? On the left side, you notice we can cross reduce. This cosine and this cosine take each other out, and we'll be left with 1 over cosine x times 1 over sine x. Is that equal to 1 over cosine x times 1 over sine x? Is it? Absolutely. So we've been able to verify the given identity. Alright, let's take a look at question number 5. What if we are to verify the identity 7 plus tan square beta is equal to secant square beta plus 6? Okay, so in this case we will have to use the Pythagorean identity, because we have squares and we have pluses. Okay, so anytime you have pluses and minuses with squares, think about the Pythagorean identity. Now we just have to pick which one we want to use to convert into the other. We can write secant in terms of tan or tan in terms of secant. It doesn't really matter. Let me show you the identity that I have in mind here. I have 1 plus tan square x is equal to secant square x. So I can replace secant with 1 plus tan square x, or I can replace tan with secant square x minus 1. So let me show you what I can do here. I want to change the left side, okay? It doesn't matter what side you change, you will still achieve the same goal. I want to get tan square x isolated. So to achieve that, I'll have to subtract 1 from both sides. So I'm going to have the identity tan square x is equal to secant square x minus 1. Okay? So we're going to make a substitution here. We're going to have 7 plus, instead of tan square x, I'm going to have secant square, not x here, we have beta. That is our variable, secant square beta minus 1. Okay? So I want there to be only secant square betas in our equation so I can prove the identity. Alright, so what do we do next? We just distribute this plus. Okay, nothing changes. So we have 7 plus secant square beta minus 1. Is this equal to secant square beta plus 6? If you combine 1 and 7, negative 1 plus 7, you get 6. So secant square beta plus 6, is it equal to secant square beta plus 6? Absolutely. We've been able to verify the given identity. Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your study of trig identities, do give us a thumbs up. Your positive feedback is very valuable to us. We'd like to have your feedback on this tutorial. If you have any questions or comments, just place it in the comment section below, and we'll be more than glad to respond. We update tutorials to our YouTube page on a weekly basis. If you like updates on our uploads, do subscribe to our channel for notification of those uploads. More tutorials and tools to help you master Precalc and Trig can be found on mathgotserved.com. You might want to check it out. Thanks again for watching and have a wonderful day. Goodbye.